My name is Changwan, and I'm a machine learning engineer at Google, working on automatic speech recognition. And today I'm going to talk about how to train an agent, how to train a machine to play the game of Street Fighter 2 in the hope that it can show superhuman performance using a technique called reinforcement learning. Why do I work on this? This is my 20% project at Google, and I spent weekend and vacation time last year working on this. Why am I interested in RL? First of all, I want to apply it to speech and LLM domain, especially in how we decode a sequence of symbols. The second reason is that I am really interested in humanoid application. I don't want to fold clothes when I do laundry, and that was my main motivation to start working on machine learning about 5 years ago. Also, RL can exhibit superhuman ability. I know, ChatGPT and Gemini took the world by the storm last year and showed superhuman intelligence. And we are trying to add new modalities such as audio, image, and video. And there are people who try to ground languages to complicated sequence of actions, like robots. But what if there are real-world problems as complicated as the ancient game of Go? Then the LLMs, or large models, might not be enough, and RL will still matter. In that context, Street Fighter 2 is a simple but very complex multi-agent RL problem. Let me tell you a brief history of Street Fighter franchise. It was made by Capcom in Japan. Street Fighter 1 was not very popular, but Street Fighter 2 World Warrior in 1991 was a great success. You could choose from 8 different characters, but it was too glitch. And then Street Fighter 2 Champions Edition came out in 1993, and it was a worldwide hit where you could choose from 12 characters. There are some tier levels, but it was pretty well balanced, and it was extremely stable. There was no serious bug found in last 30 years or so. And there were sequels, and if you have a Nintendo Switch, you can play 12 different variants of classic Street Fighter 2 in one collection, and for some games you can play online. Now more on Street Fighter 2 Champions Edition, or SF2 CE. As I said earlier, there are 12 different characters, but not all the characters are made equal. There is a tier list of characters. Guile and Bison are at the top, followed by Ryu, Sagat, and Vega, according to a Korean website called NamuWiki. People still play this game online. On Fightgate is one such platform, and it is completely free. Wei-chan, sorry if my pronunciation is not correct. The yzkof.com is a Chinese platform that is massively popular with 500 players online at any time. The game did not change for the last 30 years, but the gameplay has evolved a lot. There are now infinite combos, CPS, reverse guard at corners. Some of the weak characters, such as Honda, Zangief, and Balrog, got rediscovered. So what is reinforcement learning? It is the science of decision making, and it's about learning optimal behavior in an environment to obtain maximal reward. The agent interacts with the environment and observes reward, observation, and then take actions. This makes a full cycle. The agent dynamically learns through these interactions how to take better actions, and a policy represents distribution of actions at any given step. There might be some hidden states in the environment that are not observable. There are offline, online, continuous action versus discrete actions, and there are so many different variations this setup. Let me talk a little bit about Gym Retro environment. A little bit of history here. Originally, Deepmind, now Google DeepMind, used DQN algorithm on Atari games. But my understanding is that it was not published at the time. Later, OpenAI created the first open source version for Atari games and called it OpenAI Gym, and it was Numpy based. Gym Retro is an extension of this OpenAI Gym for retro games and is emulator based. You can play Sega, Atari, NEC, and old Nintendo games. It is no longer maintained, is now succeeded by what's called stable retro, but it's a story for another time, and back to the Gym Retro. So the Gym Retro runs this emulator and generates screenshots in NumPy array format as observation. On top of this, the screenshot, the observation also has additional status information such as win, loss, draw, and hit points of the two players. And you get this information from the memory dump, and Gym Retro has a tool to locate the specific address for this type of information. And by the way, there is no sound in the observation. Then what is Street Fighter 2 environment? It is Gym Retro on Sega Genesis emulator. This version is slightly different from the arcade version. The graphics isn't as crisp as the arcade version, and it has some quirkiness in movement, such as Vega rolls 3 times instead of 2. And the environment is wrapped as DMEMV or Deepmind environment for Acme, which is an open source RL platform that I'm going to talk about later. As you can see on the picture on the right, there are 9 different directions and 6 buttons, so in combination 576 discrete actions for 1 player per frame. And there are 2 players. And in terms of trajectory, 1 round consists of 99 seconds on the screen, but the game clock goes 50% faster than the real clock. So it's actually 66 seconds in real time. The number of possible trajectories is really large as the number of possible games in the game of Go. And they say it is greater than the number of elements in the universe. So the first thing I had to do was to reduce down the action space to 81 per frame by only allowing 6 individual button presses and all punches and all kicks. These 81 choices comes down to 1 integer per action. I know there are other design choices, such as bounded array of 3, 3, 9 in TF agents, which is another RL platform. But Acme doesn't support this, so I didn't have a choice here. And then we do some pre-processing, such as frame stacking, action repeats, dimension scaling, and grayscaling. And the environment is a synchronous environment that waits for the next action and the next observation, and so on. It is not designed to be real-time yet. The current reward design is pretty simple. My agent's hit point differential minus opponent hit point differential divided by 176, which is the total amount of HP. For example, if I hit the opponent's HP goes down, I gain some reward, and if my HP goes down, the reward can be negative by some fractional number. If the return of the sum of accumulated rewards is positive, it means a win for the current player, and a negative return means a loss. This is a very dense reward. There can be some alternative design choices. For example, we can make HP part of observation and make only win and loss generate rewards such as 1 and 0. But we didn't go that route. I've also added frame delays of 3 or 12 only to non-human or learned agents in order to emulate the response time in humans. Now this is important because without the delay, Some actions can be punished more harshly than in human gameplay. For example, if you shoot out a fireball in a short distance and your opponent can still jump over it and attack you consistently, then you will never shoot out a fireball. My current demo has 3 frames of delay, so you don't see a lot of fireballs flying around, but I'm running new experiments with 12 frames of delay, so please stay tuned. So Acme by Deepmind is the open source RL platform that I used for this project. It is based on JAX and Haiku, and it is really good for distributed RL, especially for actor-learner replay buffer architecture. I understand not all the algorithms follow this architecture. For example, Uber's Go Explore algorithm is completely different. But this Acme can be a good fit for many popular algorithms such as R2D2, A3C, and mu0. For multi-agent environments, there are at least 3 different approaches. The first approach would be multi-learner training. Literally, there are multiple learners that learn separately for each agent. But if things go wrong, there can be a complete skew and instability. I'm gonna talk about it later. The second approach would be one learner learns it all. If I understand correctly, AlphaGo, AlphaZero used alpha beta tree in Unroll such that the same learner learned from both sides of the agents. The third approach is population-based training. It is based on generations of agents and agent pool. DeepMind's AlphaStar and OpenAI 5 for Dota use this approach. One such implementation for Acme is single-agent view environment that I wrote. As you can see in the picture on right, the idea is to wrap a multi-agent environment as a single-agent environment by fixing all the agents and exposing actions, rewards, and observations for one agent only. Okay, so the first approach I tried was multi-learner plus PPO. PPO here stands for Proximal Policy Optimization, and it is an algorithm developed by OpenAI. PPO was famously used in InstructGPT and ChatGPT. Also, OpenAI 5 used PPO in Dota experiments. Now the x-axis here is the number of actor steps, and the y-axis is the return over the eval episode for the agent 1. I've run it for 1 billion frames in this experiment. As I mentioned earlier, a positive number means a win for the agent 1, and a negative number means a loss for the agent 1. But as you can see, the graph stays below 0 most of the time. That means agent 1 never had a chance to beat agent 2 after a few steps. The gap does not seem to narrow. When we have a complete skew like this, it is almost impossible to overcome it. So the approach number 1 did not work. It could be due to the multi-learner approach, but it could also be due to the PPO algorithm. PPO is mostly suitable for continuous action problems and is more effective when you're fine-tuning weights. So all the other approaches I've tried uses population-based training, so let me explain a little bit. How do we go from one generation to the next generation? We start with A0 and A1. A0 is a no-op actor. It doesn't do anything at all. A1 is a uniformly random action actor. These are the baselines we start from. Then we train A2 against A0 and A1. A2 is not very strong yet. A3 is trained from scratch against A0, A1, and A2. This goes on and on. After some point, we do the same, but limit the number of agents to k. We advance to the next generation when these criteria are met. Number 1. Smooth eval return plateaus or reaches 20 billion frames. Number 2. Smooth eval return is over 0.4. When this value is higher than 0.0, we win more than we lose. 0.4 is quite a large number actually. The second approach was population-based training plus R2D2. R2D2 is the algorithm from Deepmind in the paper Recurrent Experience Replay in Distributed RL. R2D2 is also, coincidentally, the character from the Star Wars. It is based on LSTM and prioritized experience replay, and it works with partially observable MDP to some degree, which is really nice property. The algorithm is similar to DQN, but predicts Q values not only based on the current observation, but also based on the history of observations, actions, and rewards. Using LSTM, as you can see in the picture on right, we predict the next hidden state and Q value from the previous hidden state and observation. There are also some details such as n-step look-ahead, burn-in, and other stuff. You can read the paper if you're interested. Now there is some criticism to the algorithm. For example, it can reinforce wrong current behavior and get trapped in a local maximum. That's the reason why there is another algorithm called NGU that extended R2D2 by adding an intrinsic reward. By the intrinsic reward, I mean they added some extra reward to increase exploration. The architecture for this R2D2 experiment. I used a single TPU with 8x8 topology and 2048 CPUs without inference server, and then 3 CPUs for replay, counter, and evaluator. So I have to admit that this is very CPU intensive, and it is due to the nature of the Gym Retro environment. The Gym Retro environment does not support multithreading. And the input is basically 64, 64, and 3 for screenshot observation. It is reduced dimension, grayscaled, and stacked 4 times. The frame stacking is from the DQN paper. Then we have action and reward as part of the input as I mentioned earlier. And the batch size for learner is 1024. The learner has roughly 4 components. The ResNet torso effectively reduces the amount of observation through convolutional network followed by a residual network and a layer norm with an MLP at the end. OAR embedding is for observation, action, and reward. It just concatenates the reduced observation, action, and reward. Then we have an LSTM in a dueling MLP structure. The dueling MLP architecture came from the DDQN algorithm to predict value and advantage functions separately instead of predicting Q value as one function. With this setup and with some TPU optimization, it takes 48 hours to train for 20 billion frames for one generation. These are a bit outdated graphs, but when you are only training Ryu versus Ryu, the episode returns look like this. A2 is trained against A0 and A1. You can achieve 99% win ratio after only training for 85 million steps. A3 is trained against A0, A1, A2, and you can achieve 99% win ratio after 100 million steps. But it gets significantly more difficult as we go down the generations. For A4, it takes 500 million steps to achieve 99% win ratio. But for A5, even after 1 billion steps, you can only achieve 95% win ratio. It is more difficult to train when you train for all 12 characters. Note that we don't give the information of which characters are playing. So this is at least 12 times or 12 square times more difficult problem to solve. And it gets more significantly difficult to train as we go down the generation, as we saw in Ryu versus Ryu. But in the end, I trained up to A11. Now I'll end this video with a demo. Thank you so much.